Welcome to the Explainer. If you've ever dropped your phone, and who hasn't, or just looked up at the moon, you've seen gravity in action. But what is it really? Today, we're going to dive deep into the whole idea of gravitational fields, giving you absolutely everything you need to know to nail this topic in your A-level physics exams. All right, here's the game plan. We're going to start with this idea of an invisible force. How things can pull on each other without touching. Then we'll hit the math with Newton's big law. After that, we'll pin down exactly what we mean by gravitational field strength, or G. Then comes the fun part. We'll use all this to tackle some real exam questions. And finally, we'll zoom out and see why this stuff is just so important. So, first things first, we have to get our heads around this fundamental puzzle that honestly baffled scientists for centuries. Think about it. We see the effects everywhere. The tides, the planets orbiting the sun, the fact that we're all stuck to this planet and not floating off into space. But how does that force actually travel across the huge, empty vacuum between the Earth and the moon? There's no invisible rope, right? So what's going on? Well, the answer, and this was a huge leap in thinking, is this incredible concept that physicists call a field. Basically, the Earth isn't reaching out and grabbing the moon. Instead, it generates something, this field, that spreads out all around it. The moon is just moving through that field. Yeah, this is a brilliant way to picture it. It's kind of like the temperature in a room, right? Every single point in that room has a temperature, even if you don't have a thermometer there to measure it. A gravitational field is just like that. It's a property that exists everywhere in space around a mass. So instead of a temperature value, the gravitational field tells us about the force. It describes the pull that any object with mass would feel if you dropped it into that spot. The Earth creates the field because it has mass, and any other mass, an apple, a satellite, you, the moon, is going to feel a force when it enters that field. And this slide right here shows the two main types of fields you need to know. On the left, you've got the big picture, the planetary scale. It's a radial field, where all the force lines point in towards the center of the planet. But on the right, if we zoom way in, like to the size of your classroom, those lines are so far apart, they look parallel. We call that a uniform field. And that's exactly why we can say gravity just pulls straight down. Okay, so this field exists, but how strong is the force? How do we calculate it? For that, we need to look at the rule book, the code that governs it all. And that, of course, is Newton's law of gravitation. Listen, this definition right here is absolute gold for your exams. You pretty much need to know it by heart. It tells us two really simple things. One, the bigger the masses, the stronger the force. Makes sense. Two, the further apart they are, the weaker the force gets. And crucially, it gets weaker fast. And here it is, the law in all its mathematical glory. F is the force we're trying to find. M1 and M2 are just our two masses. Now look at the bottom. R is the distance between their centers, and that little squared symbol is the key. That's the inverse square law. If you double the distance, the force doesn't halve. It drops to a quarter. Triple the distance, it drops to a ninth. And that capital G, that's the universal gravitational constant. It's the same everywhere. And notice how tiny it is. That's why gravity only feels strong when you have massive objects, like, a planet. All right, 3 quick but crucial things to remember about this force. First, it's a Newton's third law pair. That means the Earth pulls on the moon with the exact same force that the moon pulls on the Earth. Weird but true. Second, it's always attractive. Gravity only ever pulls. It never pushes. And third, to make the math work, we use something called the point mass assumption. For a big sphere like a planet, we can just pretend all its mass is squeezed into one tiny point right at its center. Okay, now for a really important distinction. So far, we've been talking about the force between two different objects. But what if we just want to talk about the field created by one object, all by itself? Well, that's where gravitational field strength, little g, comes into play. Think of it this way. The force, F, is the actual interaction, the pull that's felt between two specific masses. But the field strength, G, that's a property of a point in space. It tells you how strong the gravitational field is at that exact spot, no matter what you put there. It's the force per kilogram. And here is the formal definition you have to know.
Gravitational field strength, G, is the force exerted per unit mass. That's why we measure it in newtons per kilogram. Right here on the surface of the Earth, G is about 9.81. That means for every 1 kilogram of stuff, gravity pulls on it with 9.81 newtons of force.
Now, this derivation is a total classic, and it's just so elegant. Watch. You take the simple formula for weight, F equals mg, which you've known for years, and you set it equal to Newton's big universal law of gravitation. See how the mass of the small object, the little m, is on both sides? It just cancels out. And what we're left with is this beautiful equation for the field strength, G. And look, it only depends on the mass of the big thing creating the field, m, and how far you are from its center, r.
Okay, the theory is cool and all, but let's get our hands dirty. Let's apply this stuff to the kind of problems you are actually going to see in an exam. All right, first up, a super common one-mark question. Examiners love asking for definitions. How do you answer this one for the marks? And there it is, perfect, short, sweet, and it hits all the keywords. Force per unit mass. You write that down, and that mark is in the bag. Easy. Okay, next up, a graph question. They love these too. You're asked to sketch how the field strength, G, changes as you get further and further away from a planet's surface. The absolute key here is to show you get the inverse square law. Don't just draw some random downward curve. Here's a pro tip. Mark the important points first. At distance r, the surface, you've got your starting field strength. Let's call it GS. At twice that distance, 2r, the strength is now a quarter of that, so 0.25 GS. At 4r, it's 1/16th, so 0.0625 GS. Plot those points, then draw a nice smooth curve through them. That tells the examiner you know exactly what's going on. Okay, last one. This is more of a thinking question. It's not just about one planet. It's about two. So why on Earth would there be a spot between the Earth and the Moon where gravity just disappears, where the field strength is 0? The trick to this is remembering that fields are vectors. They have a size and a direction. The Earth's field is pulling you towards Earth. The Moon's field is pulling you towards the Moon. So in that space between them, they're in a tug-of-war. And at one very specific point, which is actually much closer to the Moon because it's less massive, the pull from the nearby Moon perfectly balances out the pull from the more distant, but much bigger, Earth. The two forces cancel each other out completely. The net field strength there is 0. Okay, let's just quickly pull everything together and talk about why this all matters, not just for your exam grade, but for, understanding the universe. So, look how far we've come. We started with this simple question, how does the Moon stay in orbit? And we ended up with a powerful toolkit. You can now see how one amazing concept, the gravitational field, and one beautiful law from Newton explains everything from dropping an apple right here on Earth to the entire dance of the solar system. But, and this is a final thought to leave you with, this leads to a massive puzzle that goes way beyond your syllabus. We've just spent all this time establishing that gravity only pulls things together. It's always attractive. And yet, astronomers have discovered that our universe is not just expanding, it's expanding faster and faster. So, what mysterious force could possibly be strong enough to overcome the pull of all the gravity in the cosmos and push everything apart? That's one of the biggest questions in physics today. Thanks for watching.